Welcome everybody. In the last class we started off with studying logic and we had looked into several of the propositions and the conjunctions and the disjunctions. So as a continuation to the previous lecture, in this lecture we will look into conditional, biconditional and related questions. And having mentioned that, let me just start off. Now, first and foremost thing, you will have to know that conditional statements are also referred to as implications. So this is also mentioned as implication. And the statements are of the form if P then Q. Now the most important aspect here is to understand how exactly this is obtained. In other words, how the result can be extracted from a statement such as this. And more so, it is represented in the following manner. And the representation is as follows. So we represent it as P, an arrow, a straight arrow like this, Q. So this is how you need to place. The arrow should be straight. And the best way to understand this particular conditional statement is through a real life example. I will give you a real life example and then I will also give you a shortcut. So a statement, if you drive your car at 90 km per hour, then you get fined. If you drive your car at 90, so this is one statement, then you get fined. So this is my P and this is my Q. Let us draw the truth table and see how it works. So it's P, this is Q, P implies Q. So the truth values are always taken like this, T, T, F, F, T, F, T, F. First case, T and T. You have driven your car at 90 km and you have received the fine. T and T, this is the outcome. There is no question in this. You have done this act. This is true in your case and you have been fined. This is also true in your case. So you get this. Second case now. You have driven your car at 90 km per hour. This is true in your case, but you did not get fined. How is it going to be possible? The first statement is you had committed the crime, but you've been let scot-free. So T and F is going to be resulting in F. So that means you are telling, or when I say you, it means the individual is telling a lie. So this is not going to be happening. The next case, the third case is F and T. You have not driven your car at 90 km, but yet you are getting fined. Well, the reason for your fine can be many reasons. For example, you would have jumped the red light. This is one scenario. So in that case, if you are actually not driven your car at 90, yet you're getting fined, and the outcome is going to be yes, that is going to be true. The possibility is there. Next case is you have not driven your car at 90 km and you did not get fined, of course that's going to be true. The reason is this has not been committed and you've not been fined, so naturally it's going to be true, right? So this is the table. Now I will teach you a shortcut when we are doing problems so that you can remember that. Okay, so having given you the truth table, there are a few important things I wish to mention here. Now sometimes they will ask you the necessary and sufficient condition for the implication statement if P then Q. Now we have taken this illustration. If you drive your car at 90 km, then you get fined. I would like to ask you which forms the necessary condition and which forms the sufficient condition. If your answer is P is the sufficient condition, the first part is the sufficient condition and the second part is called the necessary condition. Now why do I state P to be the sufficient condition? To be fined, it is just sufficient for you to hit the speedometer 90. The minute your speedometer touches 90, that is alone sufficient to be called you a person who has breached the law. That is what is called as the sufficient condition. So you don't have to do something more big or more terrible. This is sufficient enough. One breach. And what is Q? We are calling Q to be a necessary condition. Once you commit this, then it becomes necessary that you be fined. There is no other way or no other escape. So once you break the law, it becomes necessary that you face the consequences. So that is what we call it as necessary. So have this in mind. Now I have promised you that I will give you a tip. With this tip, you can handle any conditional statement. Now that tip is, have this in mind. Whenever you have T going to F, the outcome will always be F. All that you need to remember in this case for designing the truth table is this: when T goes to F, outcome is always F. So if P has a value T and Q has a value F, then the outcome for if P then Q is going to be F. So that is what you need to remember. T F will always produce you F. You don't have to remember anything else. Anything else will always be true. True, true. The only place where you will get F is over here. I hope you remember this. So I will just demonstrate how exactly this is put in use. So the understanding is, if T then F, what is the outcome? The outcome is always going to be F. So you need to get this set. Once you have this understanding, the table can easily be obtained, because all of the other outcomes are going to be T, T, T. There is only a change over here. If T, then F. What is the outcome? The outcome is going to be F. So that's why I gave you this hint. So having given this hint, let me just move on to biconditional statements. In biconditional statement, let me write the definition. A statement of the form P if and only if Q. Such statements are said to be biconditional and denoted as P. The arrow is drawn in this fashion. P can occur if and only if Q has occurred. So that's a basic understanding. Now let me draw the table and give you the outcome. Now there is an easier way to understand this. Apparently if you see the table, it might be a little bit daunting to understand. So we take T, F, T, F, and then we will study the outcome. Now this is the example I'm going to give you. A triangle is equilateral. So this is P. This can occur if and only if all its angles are 60 degrees. So this is my Q part, all its angles. So a triangle can be equilateral. A triangle is equilateral if and only if all its angles are 60 degrees. So this is what we call it as the biconditional statement. Now let me give you the outcome, and then I will explain to you the table. I will just dissect this table and show to you how exactly we can get this. So T and T is given as T, T and F is F, F and T is F, F and F is T. I will show the entire dissection here. So when we mean biconditional, what are we exactly trying to infer? We are trying to infer that this is the first part followed by this is the second part. So there is this first part occurring followed by a conjunction of the second part. That is the understanding you should get here. So what I will do is I will just show the outcome to you here. So let me draw the table. Okay. So we got P, Q, P conditional Q, Q conditional P, P biconditional Q. So remember, I gave you a tip. T going to F is always going to be F. This is the tip I gave you. Now with this tip, we can do wonders. So this is T, T, F, F, T, F, T, F. Check for T going to F. Where is it? T going to F, the outcome is going to be F. The other things are going to be T, T. So now the other way around. Q conditional P. So this is going to be the leading column. So check for T going to F. T going to F. You got a T. No, T going to F. So T going to F is going to be F. So other quantities are going to be T, T, T. Right? Now, when you see a biconditional, as I mentioned to you, this is nothing but P conditional Q conjunction with Q conditional P. Now, when you say conjunction, we are actually multiplying. Whenever you have a T, it is taken as 1. Whenever you have a F, you're taken as 0. So perform a conjunction here. T conjunction T, okay, that's going to be T. 0 times 1, that's going to be F. T times F, 1 times F, that's going to be 0, that's going to be F. T and T, that's going to be T. So this is going to be the outcome. And this is absolutely correct. And this is what we have seen here. T, F, F, T. Right? All that I did is to use this magic tool, or I should say the tip, the power breaker. Okay, so let's move on. Now the next concept you will have to know is what is called as the converse of conditional statement. Let me write that down here. Converse of conditional statement. If, let us just consider this example. Let P conditional Q be a conditional statement. Then if they are asking you to obtain Q conditional P, then Q conditional P is called the converse of P conditional Q. Example, if Shaman is rich, or I would say if Shaman is a businessman, then he is rich. If Shaman is I want to place an here, business man, then he is happy. So you have a conditional statement here. If Shaman is a businessman, then he is happy. P conditional Q. So this part is P, the other part is Q. So what would be Q conditional P? I would say if Shaman is happy, then he is a business man. You follow me? This is a lovely example. Next comes inverse of conditional statement. So let me just take this illustration. Let P conditional Q be a conditional statement. Then the inverse of the conditional statement. So you will have a negation here. Negation P conditional negation Q is called the inverse of P conditional Q. So let me give a good example for this. If you learn then you will win. It's a simple statement, right? If you learn, then you will win. or then you win. It depends whatever you want to state. But of course, this is going to be Q and this is going to be P. So this is my P conditional Q. So there is a condition that if you learn, then you win. In fact, I don't want to place this WILL. This is fine. If you learn, then you win. So what would be the negation or the inverse of the conditional statement? It's simple. If you, it's going to be if you not learn, then you do not win. There's a not there. If you not learn, then you do not win. Now the next one is called as contrapositive of conditional statement. So how does this work? Let me start off like this. Let P conditional Q be a conditional statement. Then you take the negation of Q, conditional negation of P is called the contrapositive for the conditional statement if P then Q, right? So the best example we can obtain it from the limits. So this is the example I'm giving. If f of x is differentiable, then it is continuous. So this is the conditional statement. If f of x is differentiable, then it is continuous. So in the case of contrapositive, what we need to do, we need to start with the negation of this. So that would be if f of x is not continuous, then f of x is not differentiable. So that is the illustration, and we will move on. So we got a beautiful question. Let's do this question. The question wants us to show that P conjunction Q conditional P disjunction Q is a tautology. Now, this is a beautiful question. Whatever we have studied so far is embedded in this question. So let's draw the table. So this is for P, Q, Q, and then for the conjunction, and then for the disjunction, and probably I'll draw a bigger one, and finally for the tautology. This is P, Q, conjunction, disjunction, conditional, P disjunction Q. Remember, T going to F will be F whenever you are applying the conjunction, or I should say when you are applying the conditional. So let me start here. This is T, F. This is the table that we are using, F and T, and this is F, T, F, T. These are the values that we are taking in. So P conjunction Q, that would mean T is 1, F is 0. So 1 into 0, that's going to be 0. That's going to be F, 0 into 0, F, 1 into 1, 1. And this is going to be plus, right? So 1 plus 0 is going to be 1, 0 plus 1, 1, 0 plus 0, 0, 1 plus 1, 1. Now we are going to be looking at the conditional, this versus this. So look for this hint which I've given you, or this tip which I've given you, T to F, the outcome is going to be F. So find out if you have anything in this fashion. No, you don't have T going to F at all. So all the other things is going to be T, T, T. So this would mean P conjunction Q, conditional P disjunction Q is a tautology. Hence proved. Now you can simply state hence shown. So that's a lovely question. So we move on to the next one. So we got a question. Is the formula tautology? They're asking us this question. So what is the formula given? P conditional, P conjunction, Q conditional P. So there's a converse there. So we need to obtain and see the truth values, how they are. So let me just draw the table. I know the space is a little bit restricted in nature, but I'll try to squeeze it in. Got the P, Q, So let me split it in the following fashion. So I've got a P and I got a Q. Then I need to take Q conditional P. That's fine, I can extract that. And then after I have done that, I have to take P conjunction Q conditional P. That's fine. And then conditional P conditional of this entire quantity. That's going to be P conjunction of Q conditional P. Right? There are two brackets there. So the values, I'm going to take the following values: T, T, F, and F, T, F, T, F. So let me complete the table first. Okay, the table is completed. Now this is Q conditional P. So we start this to be the leading column and we are looking for our tip. T going to F is always F. So let's apply our tip and look for T to F. Is there a T going to F? Yes, T going to F, this is going to be F. Is there a T going to F? No. The rest of them is going to be T, T, and T. Now you have to form a conjunction between P and this column. As I mentioned to you, conjunction is similar to product. So 1 multiplied with 1, I get 1. 1 multiplied with 1, I get 1. 0 multiplied with 0, I get 0. 0 multiplied with 1, I get 0. Now I need to obtain P conditional of this entire quantity. So look for the tip. T to F is F. So T to F, is there a T to F? Is there a T to F? No. There aren't any T to F. Can you believe that? So the outcome is going to be T, 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 T. So this means clearly, you can state it like that. Clearly, P conditional, P conjunction of Q conditional P is a tautology indeed. And we have shown that here in a great manner. So we move on. Let's do this question. This is a beautiful question. We are expected to find if it is a tautology or not, whether a tautology or not. And we are given the following: P conditional Q, conditional Q again. And then we got a conditional with R, and then we got another conditional with R. So this is what we have got. And there is a biconditional with P distinction Q distinction R. So it's quite a lot. And we have to check this out and decide if it is a tautology or not. So what I wish to do, I would like to, you got three statements, P, Q, R. So this is P, this is Q, this is R. Then I will place P disjunction Q, and then I will have to take this with R. So P distinction Q distinction R. I'm placing a parenthesis for understanding. Now next we will have to obtain the conditional values for this P conditional Q, and then I will have to find P conditional Q, and after that I have to take this, right? Let me consider this entire quantity as alpha, and this alpha will have to, because we don't have space, is checked for alpha conditional R, and after getting this we will have to check. If I were to take this as beta, then finally I will have to say beta conditional R. And it's not even finally, because we have just obtained this. Now after we have got this, we will have to check the biconditional, right? So we will have to check for two ways. Now let me take this as some capital X. So I will finish this off, and then I will have to check for X conditional, this quantity, this entire quantity we have got. Probably I will take this as gamma, something like that, or if the symbol capital Y, I think, is a better one. I'll take this as capital Y. So if we want to check this biconditional, we will have to check X conditional Y and then Y conditional X, and then perform a conjunction. So what I will do is I will just write over here, I will follow this because the space is too limited. I will perform X conditional Y and then Y conditional X, and then this is going to be X biconditional Y. So I will draw the table. I wouldn't be able to draw the intermediate lines because there will be too many intermediate lines. I will just draw the divisors or the division lines. Probably if I would have been a little bit more aligned, then we could have fit in these X and Y conditional statements also, but it doesn't matter. Now let me write down the truth values. So we start with T, 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 and then F, F, T, F, F, T, and then F, F. So this is the way you will have to place the values. And then you have T, F, T, T, and T, F, F, F. For R it's T, T, F, F, T, F, F, T. Now we can actually easily obtain the truth values. Now if you are going to start with PQR, you can start with TTT and then flip a T here, and then subsequently a T has to be flipped here, and then you can follow the pattern. It's not all that difficult. So we have got the truth values. Now the most important thing is to set up the table. We need to extract this. Now first, P disjunction Q. As I mentioned to you, disjunction means you are adding. So this is 1 and 1. 1 added with 1 will give you 1. 1 added with 0 will give you 1. 1 added with 1 will give you 1. 0 added with 1 will give you 1. 0 added with 1 will give you 1. 1 added with 0 will give you 1. 0 added with 0 will give you 0. 0 added with 0 will give you 0. Now this has to be performed a conjunction with R. A disjunction is not conjunction. So we need to have a disjunction between these two. So 1 added with 1 is 1. 1 added with 1 is 1. This is 1, 1, 1, 1, 0, and 1. Now there is a conditional logic or the conditional statement we need to perform. So if P then Q. So as I mentioned to you, we are looking for the tip. T going to F is F. So let's do that. Let's check T going to F. T going to F is F. T going to F is F. And the rest of them are T's. So you have a T, 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 and T. Now we need to perform a conditional with this against Q. So use this clue. T going to F is F. So this versus this. Is there a T going to F? T, no. T, no. No. T going to F, yes. T going to F, this is going to be F. T going to F, this is going to be F. So rest of them are going to be T, 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 T. Now this entire thing is taken as alpha, and this has to have a conditional connectivity with Q, with R, right? So I'm taking this as alpha. So this, so we need to have alpha conditional R. So again use this hint. T going to F is F. So look for T going to F. Yeah, T going to F. This is going to be F. T going to F, F. T going to F is F, and the rest of them are T, 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 T. So this is beta. Now I need to have a conditional link between beta and R, right? So this is beta. This is actually in condition with R. So if beta, then R. So look for T going to F, T going to F, T going to F, T going to F, F, T going to F, no. So the rest of them are T, 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 and T. So now we have completed the table. Now what we need to do is, I need to have a conditional with X and Y. If X, then Y. So check for T going to F. It's T going to T. So this is T, T, T. This is T, T. This is T. This is T. And this is T. And now it's Y conditional X. So the other way around, right? Instead of starting with T going to T, we have to start from this end, T going to T. So this, check for T going to F. I don't see any T going to F at all here. Is there any T going to F? No, there isn't any T going to F here. You see that? There isn't any T going to F. It's all T versus T or F going to F. So all of them are going to be T, 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 T. Now biconditional. So that means you are performing a conjunction between this and this. So obviously you can see you have only T's here. So the outcome is going to be T, 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 T. So this is a tautology. This is a tautology. And that is a beautiful question. Okay, so let's do this question. We are asked to show that P conditional of Q conditional R is equivalence to P conjunction Q conditional R. Sometimes in some of the textbooks, instead of the arrow, they are utilizing an arrow like this. So don't get worried. This is nothing but this. So we are expected to show that this part is an equivalence with this part. So both of them are equivalent. So that is what we need to show. Now we got three components. I will just show you how to obtain P, Q and R. And then you have Q conditional R, write that down. And then you have P conditional of Q conditional R, write that down. Then you have a conjunction, P conjunction Q. And then you have P conjunction Q conditional R. It looks daunting, but it's easy. It appears to be difficult, but believe me, with the tip I've given you, you can break through any logic question. It wouldn't be difficult at all. So let me draw the bare minimum table. Okay. Okay, so let me place the truth values. Now for this, you place 4 T's, 1, 2, 3, 4, and 4 F's, 1, 2, 3, and 4. And for this, you place TF, TF, and then TF, and then TF. And for this, TT, F, F, and then TT, F, F. So this is accepted. In fact, you can use the same truth values to do any question for that matter. So having mentioned that, let me go on. Q conditional R. So that would mean I will have to look for this clue. T going to F will result in F. So look for T going to F will result in F. T going to F will result in F. The rest of them is going to be T, 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 and T. Now P conditional of Q conditional R. So this is obtained, and I have to look for this key. T going to F is F. So T going to F is F. T going to the rest of them are T, T, and then T, 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 and T, right? And then P conjunction Q. P conjunction Q. Its product 1 into 1 is 1. 1 into 0 is 0. 1 into 1, 1. 1 into 0 is 0. 0 into 1, 0. 0 into 0, 0. 0 into 1, 0. 0 into 0, 0. So now it's P conjunction Q. There is a conditional against R. So look for the key. T going to F is F. T going to F is F. T going to F, no. The rest of them are T, 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 T. Now we have to check the equivalence of these two. So clearly you can see that. You see that? This is same as this. Hence, they are equivalent. So this is a lovely section, and we have studied quite a bit. We have studied in detail on concepts involving conditional and biconditional logic, and probably we will do one more question and wrap it up. Now I wish to draw your attention to one more information, which is called as negation of biconditional statements. This is very important. So what would you do if you have been given a biconditional statement and they are asking you to find the negation of this? Now I'm going to give you an easy way. Imagine we have a question. Find the negation of this is the question. ABC is an equilateral triangle if and only if its degrees are equal. ABC is an equilateral triangle if and only if its degrees are equal. So this is a biconditional statement. We are expected to find the negation. Well, what I wish to do is I would like to take this part as P and this part as Q, and then we are expected to find the negation of this biconditional. So first what I will do is I will say consider the negation of the biconditional statement. Now this can be rewritten as, now I have explained to you, the biconditional means you have P conditional Q, this is going on, and then this is actually in conjunction with Q conditional P. This is what is happening, but this entire thing is under the negation operation. So now what I will do is I will distribute this negation, and that would give me negation of P conditional Q. I distribute it on this conjunction, so that conjunction will become disjunction, and then again I'll have to distribute it over Q conditional P. So this is what I've got. So now I am distributing it one more time. So this is going to be negation of P. Now before I could apply the negation for P, what I will do is I will actually get rid of this conditional statement. Now to get rid of this conditional statement, I can rewrite this as negation of P disjunction Q followed by a disjunction and a negation. I can get rid of this conditional statement, and that would be negation of Q disjunction P. Now I would distribute this negation, and that would give me negation of negation P, and once I apply the negation in for this disjunction, this would become conjunction, and then I apply the negation to Q. That's going to be negation of Q. I already have a disjunction, so I place that. Now I am distributing this negation inside, so that would be negation of Q. I apply the negation to the disjunction, that would make it to be a conjunction, and then I got negation of P. Now negation of negation P is equal to P. This is a conjunction, and I've got a negation of Q. I place it in parenthesis. I got a disjunction. Negation of negation Q is Q, and I have a conjunction followed by a negation of P, which is nothing but negation of the biconditional PQ, or P versus Q. So this is what we are expected to find if we are asked this. So this is a lovely side note I wish to give you, so that you can apply it in the questions, because you may not know what type of questions that would come, specifically if you are going up for any competitive exams involving logics. So that completes our lecture today, which we had primarily focused on conditional, biconditional statements and how exactly we can use them in extracting inferences. So I hope this was useful, and we will meet again in the next lecture. If you have any questions, please make sure to leave your questions. If you have any recommendations for any further improvements of the lecture, you can place that, and if you want any other topics to be covered, you can also let me know. So having mentioned this, I hope you get the best out of this, and as I used to mention, practice makes you more professional, and the more you practice, the better you become. And the key is staying consistent. So thank you